Hello everyone. So in this video, we will solve the problems on the drag force and the shear stress. So basically, this is the second part in the boundary layer. So first, we will see what is meaning of drag force and the shear stress. So consider this is the solid surface. So it is a rectangular plate, and the fluid is flowing over this plate. So this is the velocity, is the free stream velocity. So when this fluid makes the contact with this plate, then it will form the boundary layer like this. It means that there is a velocity variation because of the viscosity. So we have already discussed this in the previous video. So this is how the boundary layer is there. Okay. Because of this viscosity effect, that is the mu, a shear stress is produced on the plate. So this is the rectangular. So the shear stress, it will create the force, and this force is called as the drag force, that is the FD. Okay. And basically this drag force, it is because of the shear stress, which is the tau zero. Zero means what? This is the shear stress acting at the bottommost layer, where the y value, this is equal to 0. Basically, we measure the y in this direction, and this is the direction along the velocity. So this is the x direction. So the formula for drag force. So this is for very small region delta x. So FD is equal to the shear stress tau 0 into delta x into B. So B is the width of the plate. So the complete force FD we can determine by the integration. FD is equal to integration 0 to L. So L is the total length. So this is the length L of the plate. So integration 0 to L tau 0 into B into dx. So this is the formula for the drag force. There is a second formula for the drag force. FD is equal to, it is 1 by 2 the drag coefficient CD into rho A U square. So by using both these formulae, we can determine the drag force acting on the plate. Now to find out the shear stress, at the contact layer, which is a tau 0 with the solid surface. So we have the formula tau 0 upon rho u square. This is equal to del theta upon del x, where the theta is the momentum thickness. And the formula for theta is, it is integration 0 to delta u upon capital U in the bracket 1 minus u upon u into d1. Okay. So by using this formula, if you know the value of theta, rho, and u square or u, we can determine the shear stress, that is the tau. Okay. And there is one more formula, which is a coefficient of drag. This is a CD, and the formula is, this is equal to FD, which is the drag force, upon 1 by 2 rho A U square. Okay. So question can be asked on the shear stress, coefficient of drag, and the boundary layer, that is boundary layer thickness, which is the delta. Okay, so let us see one problem. So here the question is find an expression for boundary layer thickness, which is the delta, shear stress tau 0, and the drag coefficient CD in terms of Reynolds number Re. And one equation is given, U upon U, this is equal to 2 into bracket y by delta minus y by delta square. Okay, so here we have to find out first the boundary layer thickness, second the shear stress tau 0, third the coefficient of drag, and all this delta tau 0 and CD, we need this in terms of Reynolds number, that is the Re. So if there is a question like this, first try to find out the equation for tau 0. So directly use the formula tau 0 upon rho U square. This is equal to del theta upon del x. So this is the standard formula for the shear stress. Okay. Now here theta, we know that theta is equal to integration 0 to delta u by u in bracket 1 minus u by u into d1. Okay. So first we will find out this theta and then substitute this theta in the original equation of tau 0. So theta, this is equal to 0 to delta. Now put the value of u by u from this equation. So 2y upon delta minus y square upon del square into 1 minus this u by u means, again put this value, 2y upon delta minus y square upon del square. So this is equal to integration 0 to delta. This is 2y upon delta minus y square upon delta square. This is 1 minus 2y upon delta plus y square upon del square into dy. This is into dy. Okay. Now by first term, multiply this complete bracket. So this is equal to integration 0 to delta. This 2y into 1. So this is 2y upon delta. Next 2y into 2y. So minus 4y square upon delta square, and 2y into y square. So plus 2y cube upon delta cube. Now next term is minus y square upon delta square into 1. So minus y square upon delta square minus y square minus 2y. So plus 2y cube upon delta cube, and next y square into y square. So minus y raised to 4 divided by delta raised to 4 into d1. And this is equal to, this is 0 to delta. Now just simplify this equation. This 2y upon delta will remain as it is. Now refer this term y square and this y square. So minus 5y square upon delta square. Next this y cube and this y cube. So plus 4y cube upon delta cube, and last this y raised to 4 upon delta raised to 4. So minus y raised to 4 divided by delta raised to 4 into d1. Okay. Now integrate this complete equation so that we can get the value of theta. So theta is equal to, I will again write the previous term 0 to delta in bracket is 2y upon delta minus 4, 5 y square upon delta square plus 4 y cube upon delta cube and minus y raised to 4th upon delta raised to 4. Now integrate this equation. So this is 2y square upon 2 delta minus 5 y cube upon 3 delta square plus 4 y raised to 4th upon 4 delta cube minus y raised to 5 upon 5 delta raised to 4. And the limit for integration is 0 to delta. So put this limit delta. So this is 2 and 2 will get cancelled. This is delta square upon delta minus 5 by 3 delta cube upon square plus delta fourth upon delta cube minus delta 5 upon 5 delta raised to 4. So this is delta minus 5 by 3 delta plus delta minus delta upon 5. So if you simplify this equation, then finally you will get 2 by 15 into delta. So this is the value for theta. Now this theta is nothing but the momentum thickness. Now refer the previous formula. So we have the original formula for shear stress. Tau 0 upon rho u square is equal to del theta upon del x. So put the value of theta here. So theta we got as 2 by 15. So tau 0 upon rho u square is equal to del theta upon del x. So this is equal to del by del x in bracket 2 by 15 into delta. So this is the value of tau 0 upon rho u square. From this we can write tau 0 is equal to, just take 2 by 15 out of the derivative. So it is 2 by 15 dou by delta upon dou x into rho u square. Okay. So consider this equation 1. Now for tau 0, we have another equation. This tau 0 is equal to, as per Newton's law of viscosity, mu into du by dy. Okay. So from the given equation in the problem, find out this du by dy. So consider this equation 2. So what is given? U by u, this is given as, this is 2y upon delta minus y square upon delta square. So this is given in the question. Okay. So from this, write equal to this capital U in the bracket 2y upon delta minus y square upon delta square. From this, we can differentiate du by dy. This is equal to, u is a constant. differentiate this term. So 2y upon delta, 2 by delta is a constant, and dy by dy is 1 minus y square derivative, it is a 2y upon delta square. Okay, now we want shear stress at tau 0. So when y is equal to 0, this du by dy at y is equal to 0, let's put y is 0, so it is 2 capital U upon delta. Okay, now put this value in the equation 2. So we will get tau 0 is equal to mu into 2 U upon delta. So this is equal to 2 mu capital U upon delta. So this is equation 3. Okay. Now from comparing equation 3 and equation 1, so from equation 1 and equation 3, we get this 2 by 15 rho U square dou delta upon dou x. This is equal to mu this U upon delta. Okay. Now just rearrange the term. So take delta on this side. So delta dou delta upon dou x. This is equal to, this is 15. This 2 will get cancelled. This U and U square will get cancelled. So 15 mu upon rho capital U, and from this del, this is equal to 15 mu rho U into dou x. We can write this term as delta d delta. This is equal to 15 mu upon rho U into dx. Now if you integrate this on both the sides, so from this we will get, this is delta square, this is equal to this 15 mu rho and U are constant. So this is 15 mu rho U, and integration dx will be x and plus the constant of integration. So it is a c. Now to find out this c, you can use the boundary condition. So at x is equal to 0, the delta value is 0. So from this c is equal to 0. Sorry, this is delta square by 2 integration. So we get the equation as delta square by 2. This is equal to 15 mu rho U into x. And from this we get delta. If you rearrange the term, so this is equal to the square root. You can take this 2 on this side, so it will become 15 into 2, so it is 30. So 30 mu into x divided by rho into U. So this is the equation for delta, which is the boundary layer. Now if you take the square root of 30, so this is equal to 5.48 in the square root. So the value is mu x divided by rho U. So this is the value for delta. Now we have to write this delta. The question is find out the boundary layer thickness in terms of Reynolds number. So we have to rearrange this term in terms of Reynolds number. So the basic equation for Reynolds number is, . So Re is equal to this density free stream velocity into x divided by the viscosity mu. Okay. So we will rearrange this delta value. This is equal to 5.48 the square root mu x upon rho u. So this is equal to 5.48 the square root mu rho u. Now refer this formula. This is rho u x upon mu. So multiply here by x and multiply numerator by x. So x and x, it will become x square. Now this term, this is the Reynolds number. So this is 5.48 in the square root x square divided by Reynolds number. So this is equal to 5.48 square root Re into x. So this is the equation for boundary layer thickness in terms of Reynolds number. So delta, this is equal to 5.48 square root Re into x. So this is the final answer for the first question. That is the delta. Now, by using this delta, we have to find out the shear stress. For shear stress, that is a tau 0, we have the equation tau 0 is equal to 2 mu u upon delta. So you can refer this. So this is the equation for the shear stress, which is 2 mu u upon delta. So this is 2 mu u upon delta value is 5.48 divided by square root 3 into x. So this is equal to 2 mu u into square root Re divided by 5.48 into x. Now you can simplify this value. So this is the equation for tau 0 in terms of Reynolds number. So this value, this is equal to 0.365 square root Re mu into u divided by. And the third part in the same question, it is about the coefficient of drag, which is the CD. For that, use the formula CD is equal to FD upon 1 by 2 rho AU square. And first calculate the FD value. This is equal to integration 0 to L tau 0 into B into dx. Now put the value of tau 0 that we have just calculated. So 0 to L 0.365 mu into capital U into square root Re divided by x into B into dx. Now here Re, it has the value in terms of x. So it is integration 0 to L 0.365 mu capital U upon X, and RE is rho U X upon viscosity mu into B into dx. So FD is equal to 0.365 into mu into capital U. All these are constant into square root rho U upon mu into root X is in the integration 0 to L divided by X. So root X means this root X and divided by this X into B into dx. B is also constant. You can take out of the integration. So this is equal to. So I will take this including the B as a constant. So I will write here as a K. So integration 0 to L 1 upon root X into dx. Okay. 1 upon root X is X raised to 1 by 2. Take in the numerator. So X raised to minus 1 by 2. So K into 0 to L X raised to minus 1 by 2 dx. So K, now integrate this term, X raised to minus 1 by 2 plus 1. So it is 1 by 2 divided by 1 by 2. Integration 0, limit is 0 to L. So K, if I put here, so this is L raised to 1 by 2. So it is square root L divided by 1 by 2. So this is the value of FD, which is the drag force. So just put all the values for K. So finally, you will get the answer as 0.73 B into mu into capital U in the square root rho UL divided by mu. And CD is equal to FD upon 1 by 2 rho AU square. So this is equal to 0.73 B mu capital U rho UL divided by mu upon 1 by 2 rho AU square. Now here area, so if you consider this rectangular plate, so this is the B and this is the L. So it is a B into L. So this is B into L. Okay. So from this, if you simplify, you will get the answer as 1.46 mu upon rho LU rho UL upon mu. So this is equal to 1.46 square root mu divided by square root rho UL. So this is 1.46 square root mu upon rho UL, and this square root rho UL upon mu is nothing but RE. So it is 1.46 upon RE. So formula for RE is it is a rho UL upon mu. So this is the final answer. That is the coefficient of drag in terms of Reynolds. So this is the complete procedure to find out the shear stress, boundary layer thickness delta, and the CD in terms of Reynolds.